to SciSoc's first in-person talk of the year. Today we are honored to have with us Professor Didier Queloz, who will be giving us a talk entitled The Exoplanet Revolution. Professor Didier is currently a professor of physics in the Cambridge Cavendish Laboratory and also a professor of astronomy at the Geneva University. He was awarded the Physics Nobel Prize in 2019 for the discovery of an exoplanet orbiting a solar-type star. In 1995, during his PhD with his supervisor, they announced the first discovery of a giant planet orbiting another star outside the solar system. This seminal discovery has spawned a revolution in astronomy and kick-started a field of exoplanet research. In the 26 years since this discovery, Professor Didier's scientific contributions have been great progress in detection and measurement capabilities of exoplanet systems, with the goal to retrieve information on their physical structure and better understand their formation and evolution by comparison with our solar system. More recently, Professor Didier has directed his activity to the detection of Earth-like planets and universal life. In the course of his career, he has developed astronomical equipment, new observational approaches, and detection algorithms. He has participated in and conducted programs leading to the detection of more than 100 planets. He has also been featured in numerous documentaries, movies, articles, TV, and radio interviews to increase excitement and promote interest for science in general, and particularly topics about exoplanets and life in the universe. With that, join me in welcoming Professor Didier for this talk.
I'm so glad to be here. That's my first in-person lecture since the eruption of the COVID pandemic, so it's really cool to do something with real people. I'm so glad. So what I will be sharing with you is what I do and most of the people are calling revolutions, which is a new perspective about our system as a planetary system. And also I will be describing what we're doing right now in Cambridge about pushing this to the boundary of exploring, let's call it the origin of life on Earth, and also the possibility of other life on other planets. So let's go back to the beginning, just to make sure we understand how all this started. So we all have learned essentially about planet and what is a planet from the planet of the solar system. And essentially the foundation of the whole theory of the planetary formations and understanding of the structure of this planet is essentially based on all the probes, the exploration we have made of the solar system planets. And there is something quite profound in the way the planet is built, is this idea that you have a core in the middle of the planet, and then from the core you accrete a lot of material on the top of that. This is a very specific formation scenario which makes a planet different from a star. The star, you essentially collapse a lot of gas, the hydrogen, you have plenty of hydrogen in the universe. The planet is a building mechanism where you form a small core, and then from that core you accrete more and more and more, and that's how you make your planet. So because of this formation process, which is valid for any planet, even the one Neptune's, and well, essentially for the Earth you have only the core, we have an understanding and expectations what must be the other planet orbiting other stars. And what has happened was a complete surprise, because while we were expecting to have planet on another star, and people have been looking for that for years and years and years, the planet that we have detected in the last 20 years doesn't really fit this kind of model that we have based on the solar systems. And the reason why it does not fit is because of the formation mechanism of a planet related to this core structure. So to give you an idea how you form a planet very quickly, this is one of these beautiful pictures that we can do in astronomy these days using what we call a radio millimetric telescopes, about the wavelength of your microwave here. And what you see is the thermal emissions. It's not very warm actually. This is, if you have the 0 degree as minus 276, this would be about 60 degrees above the zero. So it's very, very cold to our Earth standard. And that's the irradiations, the thermal radiation you have when you're forming a planet. What you see here is what we call the dust. all the dusty small particles you have around it, and you see there are structures, kind of grooves, and the story behind this is an ongoing formation process of a planet. So this beautiful picture is one of the very nearby stars around us. The age of the star is 10 million years. So remember, all the scaling of the age is kind of a little bit different when talking about in the astrophysics. So the age of the solar system is 4.5 billion years. So this is just very, very young stars. This picture tells us that the planets are being formed at that stage. What we don't see here is the main component of the planet is a gas. And the gas is not visible on that picture. To see the gas, you have to change a little bit the perspective. So what I will be doing here, I will look at the disk using another star, which is well known, which is Beta Pictoris, where we have the disk which is being seen just on the edge. So the picture on the top, you have a kind of it's a dark spot in the middle, which is on purpose because we would have the star at that location here. So the system is designed to hide the star, but what you do see is the kind of reflected light from the stars on this famous disk that you have the picture before, all this kind of small dust you have. So it's a reflected light you have here, is what you essentially see almost invisible here in this picture. So what you do notice on this picture, well, if you have good eyes, you may see there is a kind of a small disk with a warp in the middle. That is because there is a planet that has been detected here that creates this warp. Twist a little bit the disk. But what you do see is the disk is very thin. So the disk of the matter, all this small particle you have, and when I'm talking about small particle, I'm talking about something that could be of the micron size, but could also be a few centimeters, a few meters. This is what we're talking about here, right? It's really all this ingredient that will glue together and form the core of the planet. It's very, very thin, and you don't have that much, actually. The more dominant material you have is the gas. To give you an example, you get a good example of all the matter is being organized in a solar system, is you have, for 99%, the mass which is being stored in the sun, and it is the gas, which is the hydrogen you have, and a bit of helium you have in. All these small particles that you have this sand grain that is made of silicate, in the case of the Earth, it's a very, very tiny fraction. So this is a very tiny fraction compared to the massive amount of the gas you have around. And what you see on the picture on the bottom, it's the very same picture with the very same scale, but from the gas. So the trick here, we are detecting the CO2. The CO2 has a very nice, spectral feature. So we're using the same kind of telescope, but really targeted on the CO2. So really, we get the idea of the strength of the CO2, and we get an idea of how much CO2 there are. And on this picture, just looking at the structure of the picture, there is something which is striking. The first things you do see is the vertical extension is very wide. So the gas is way more extended vertically compared to the dust, which is something you would expect. We call that the hydrostatic equilibrium. This is the reason why you can breathe on the mountains. I mean, there's still gas on the mountain because there is a pressure balance with the gas, while if you throw rocks from the top of a mountain, it's going to go down until the gravity will just stop the rock. So the way the gas is sustained, maintain this kind of height for the gas. So the other element, which is very fascinating, is there is a cut in the edges. So there is a distance, which in this case is about 60 AU, 60 times the distance between the Earth and the Sun, where there is no gas being detected. It's not because the equipment is not good enough, it's because really there is no gas detected. And then if you think a little bit what's happening here in the system, when you're reaching the edge of the system, well, you don't have much heat coming from the Sun. When you are very close to the Sun, it's much more energy that is maintaining the gas in a gaseous form. Well, if you get cool enough, you have a kind of a temperature gradient down to the disk. There's a point when it's so cool that the gas cannot be a gas anymore. So there's a phase transitions. It's snowing in a way, if you want. So you can do that with the water. In this case, you have a CO2. So you are making grain, dust grain. But instead of being dust grain of silicate, in that case, this is dust grain which is made from the gas. So this very, very specific moment when the gas stops being a gas and becomes solid creates something which is an avalanche. So all this material you have on the top, because it's not anymore the gas, will collapse. So since you have way more gas than material, you have way more material to build the planet on the outside. This is the reason why the big planets are on the outside. Because there are so many gas that has been transformed into solid outside, so you create this material, this big amount of material that is what we call the core of a planet, and this becomes big enough, fast enough to accrete all the rest. This is why we have the giant planet outside. So this is a basic reason why everybody was expecting every planet to look like our own system. Because of this reason, actually. It makes a lot of sense. There's a lot of good sense behind all that is physics. Now, you can imagine the big surprise when we announced the first planet that is of the kind of Jupiter, but instead of being at the location of Jupiter, where was orbiting very close to the stars. And nobody would, I mean, at that time, I think nobody believed us, essentially. It was kind of a 2-3 years a bit difficult for me, especially for me because I was very young at that time. Because we had the feeling we did something great and we did it right, but the community could not believe that. It was too big. It has too much impact on the formation theory until people realized that there are a couple of ingredients that people have forgot. And the main ingredient that was forgotten in this process is when you form a planet, there is still a disk around, and there is an interaction between the disk and the planet. And this interaction is dramatic and can change completely the location of the planet. Then comes the interesting question, so why then in the solar system we have not moved around? And essentially we don't know yet. So 25 years later, we have this picture that gives you the kind of overview what we have learned about the exoplanet. I just use 3 parameters here. This is all data. There is no modeling here. This is the size, the mass, and the period of the planet orbiting other stars that has been detected in the last 25 years. So this is really the collection of all this data. There is 2 techniques being used essentially to detect these planets. Well, one of them is related to measure the radius, called the transit, when the planet goes in front of the star, you get the size of the planet. The other one is when you get the mass of the planet, you use the fact that the planet orbits the star is moving around, and then change the speed. And that's what we've been using to detect the first planet, 51b. Now, what you do see on this picture is there is essentially 3 groups of planets that's been found. The one that we call the hot Jupiters, where the first planet belongs here. Another one that seems to be almost similar to Jupiter, but pay attention to the scale here. This is 300 times the mass of the Earth, which is 1 Jupiter. But then when you move 1 scale up, it's a factor 10. So we have much more massive planet than Jupiter. They exist in a more massive way, and we don't really know where to stop, because there's a point it becomes a star again. It's too massive, and it starts to emit the thermonuclear reaction here. So, and then the big surprise was this population of planet here, which has a size of between the Earth and Neptune, or mass between the Earth. This is also Earth mass here. It's 1, 10, 100, up to Neptune's, whatever you want to mass of the size. And this population of planet was absolutely not expected. So that one clearly not, and that one either not. Now, what's happening here is we have this striking element that, well, the solar system seems to be alone here. We don't have any more planets there detected, except us, and that one as well. So we have to be careful here, because the technique we've been using has some limitation in terms of detections. And if I help you a little bit, this is the kind of a limit where we can detect anything. So anything on the left side can be detected, anything on the right side can't be detected. So maybe we have plenty of planets there and there, but we don't know, because we cannot detect them yet. It's very difficult. So we're working very hard to detect this planet right now. There's a lot of technical problems you have to fix. It's very tiny, so the impact on the stars becomes very small, and the problem is the star doesn't cooperate, because there is some atmosphere of the stars that start to vary, and everything starts to mix up. It becomes quite complicated here. Now, what is interesting, aside the fact that we have a region of the diagram that we don't know, especially this one, which is of high interest for us, is we can still do some statistics here. And you can ask yourself, if I have a star, what is the occurrence to have a planet orbiting that star? And it's quite complicated, and there is a lot of, some disagreements exactly how to do that, because you have to account for the systematics on the way you pick up your stars. It's quite complicated, but people would agree with this kind of a range of occurrence for each of the planets. So there's a very few, between 1 to 5% of this famous hot Jupiter. So they're very rare. They're fascinating for us because the story started there. We started to pick up this one because that was the easy one to pick, essentially. We had 150 stars. We had actually 200 Jupiter into the sample. So people keep telling us we are lucky. Actually, no, we were not lucky, but just the fact there are a few percent of this system, so we had to find some. We were the first one to look in a systematic way on so many stars, so it was not a miracle why we found this object. We've been lucky in a sense because nature is nice with us, and nature has produced planets that were not supposed to exist, and it is making us very successful. Otherwise, if we would only stick with a system like the solar system, we would not have very much, because we'd be only detecting this Jupiter. All the other, they're completely unexpected. Now, the hot Jupiter, the Jupiter, is about 10 to 20%, so it's an interesting number, because if you reflect to the solar system, you can say, well, maybe we do see a system like our own. It's partially true, because we're talking about most of the planets being slightly shorter in terms of period. Most of them have an eccentric orbit, so they don't really fit with any planet in a range of the systems. And if you look at the mass, most of them are more massive than Jupiter. So we're not very sure we can compare with the solar system, but if you ask me whether there are kind of a Jupiter twin already found, I can answer yes, there is a couple of them that we've detected. But we have no idea whether there are small planets orbiting in this system. But the big surprise is this, what we call the super Earth or mini Neptunes here, because the occurrence, the likelihood that when you observe the stars, and think about that, we don't see stars tonight, but when you see stars, think about all the stars you see. Each of the stars, with a chance of 1 out of 2, have a planet like that, which is a planet that doesn't exist in the solar system. We don't have any planet in the range of the mass of the Earth and Neptune's with a period of 10 to 20 days. The closest we have is Mercury, but it's a very tiny planet, and it's farther out. It would be 60 here, so that would be much farther out. So we have really planets that were absolutely unexpected, and this is what I call the gift of nature, because without this system, we would never have been so successful in terms of community and growth of interest for the topic, because this is really fueling the field of exoplanet right now. And of course, because we're detecting planets in the range of the mass of Neptune, we're asking a lot of questions to ourselves. I mean, what does it mean? I mean, how can we compare with a planet like we have in the solar system? So 50 to 80% means practically that it leaves some room for maneuvering for finding the planet like the Earth, but not that much. So we can already conclude something. If you ask me what is the main conclusions about 25 years of exoplanet discoveries, is we know that the solar system is not the dominant populations of planets in the universe. It is one amongst many, but it's certainly the most dominant population. The most dominant type of planet is this one, which what we call the compact, nearby, Earth-like, Neptune-like systems. So that was a big shock about this. And if you ask me why exactly it is so, we don't really know right now. And the way we are making progress on that is trying to dive into the astrophysics of this planet. How do we do that? Well, there are blue dots and red dots. The red dots mean is detected by the radio velocity techniques. Blue is detected by the transit. If you pay attention, if you have good eyes, you will see there are some red here as well. It means some of the systems, some of the system that was detected by the transit, we managed to measure the mass as well. So you can combine the two techniques. So you have for some of the system at the same time, it's a real measurement, it's not a model here. We have a real measurement of the mass and the size. When you have this, you have access to the density of the planet. And that's one of this density plot, which tell you something about the nature of the planet you're talking about. So to help you to read that, so this is the mass, this is the radius, this is 10 times the radius of the Earth, which is Jupiter. You have Jupiter here, Saturn here, and all the point you have is direct measurement of planet that we have done, we and the community, and then you have an error bar. So the kind of error bar, I give you an idea how difficult it may be, and some of them you're not very sure exactly what is the value of the mass. 1 sigma, so you can play 2 sigmas and you see what is the regime. But you see there is a global trend here that depends on the mass and the size. So let's start on the top to understand what we're talking about. So here on the top, this is the mass of the Jupiter you have here. And to help you to read this, we have added to the diagram with this dotted line here, the model of a Jupiter structure. So the structure of Jupiter we know, we can compute what's called the global density of the planet. And if you understand the structure of Jupiter, you can remove the mass and see what is the change into the radius. So this is a change of the mass radius for a system that is like Jupiter in terms of structure. And you see it's matching, of course, Jupiter, Saturn. We do have some object that is fitting this regime, but most of them are clearly above. So most of the planets we have detected that is in this regime seems to be above, so they have higher radius. So if you increase the radius and keep the mass the same, you will decrease the density. So actually they have less density, far less density. Some of them is quite dramatic because they could have a radius which is 2 times larger. So the same mass than Jupiter, but 2 times larger. So it goes to the cube, to the power 3, sorry. So you can have an idea of the density, or the density is really weak on some of the system. So the reason why, because they're very nearby the stars, so there is a lot of energy coming to the surface of the planet and is changing something into the structure of the planet. We're not sure exactly what, but the structure of the planet is affected by this. Well, we can keep going down, and something is interesting here. When you reach the mass of Neptune, this is Neptune, you don't reproduce Neptune with the model of Jupiter. Which is fine, because we know that Neptune is a kind of failed Jupiter. So you have to imagine Jupiter had enough time to capture all the gas around. Neptune was a bit too far away in the system, had not enough time to do that, and the gas, which is unstable at the formation of the system, vanishes. And after 20 million years, when you form a system, you have no gas anymore. So what happened, you have the core being formed, and you have the core trapping all the gas, but then if you're not quick enough, you don't trap all the gas you want. And then you stick in a situation where you end up like a Neptune. So Neptune is denser because there is less light gas. So essentially it's Jupiter, you remove the hydrogen. So if you remove the hydrogen, you're not far from Neptune, and this is why it's denser. And you have to help you a little bit of kind of a similar density, which is a bit of a trick here, because it's a water planet. So if you use water as the molecules, but you use the structure of water because we know quite well the water under very high pressures, and it's being studied for the Earth actually. And you can predict where you would sit if you have a planet only made of water, which doesn't exist because you still have the core and which is denser, but to give you an idea. So we do have a whole series of planets here that goes down to 2 Earth mass. So you can have a mass of a planet of 2 Earth mass, but it's not a planet like the Earth. It's a planet like Neptune. So that's a kind of interesting conclusion. And you have even planets that have the mass of Saturn, which is not a Saturn, which looks more like a Neptune. So you realize that the range that explore nature when they're forming planet is way wider than the perception we had. We have this kind of stepwise approach between all the different kind of planets. We used to learn the giant and the ice giants and then the typical planet in the solar system. When you see that more globally, it's just not true. There is a continuum here, depending on the history of the formation of this planet. And then you can make a jump, and you go to the Earth. So you use the Earth density, which is this green line. So Earth is 1,1, just here. You increase the mass, and we do see here that we have detected planet that would qualify as Earth-like in terms of density. It's a bulk density. Doesn't mean it's exactly like the Earth, but it has to be somewhere, something not far from the Earth in terms of bulk density. It's called the bulk density. And there is a big gap between the two. You can even see there is kind of a lack of object, which we understand as a possible consequences of that this object are very close to the star. They're so close to the stars, you can imagine that you have a planet like that, and because it's too close to the stars, there's not enough mass to retain the atmosphere. You have the energy coming from the star, is boiling the atmosphere, and you lose the atmosphere. A bit like Mars, in a way. Mars has not enough mass to keep the atmosphere. So here you have more massive planet, fewer Earth mass, but because they're too close to the star, they're losing the atmosphere. So there's a possibility that some of these planets, if not all of them, still don't know, or the end product of a planet that was like that, but has evolved. So this is really a big mystery on that. If you ask me what it is about, I think this is something that we're not sure to understand, and we would like to understand. So what we're trying to do right now, we're trying to push and trying to understand what we're talking about. So if you have to remember something about all these long explanations, is we have completely changed the understanding of the structure of the planet. We used to have Jupiter, Neptune, Earth. Right now we have all of these. So we have object between Neptune and Jupiter. We're not sure exactly what it is. We have object between the Earth and Neptune. Not sure what it is. It could be something like Jupiter, but just with a bigger core. You can have Neptune and you have it a bit smaller, so you're shrinking Neptune to a smaller object. You can remove part of the atmosphere of Neptune, you end up with being an ocean planet, and you can keep removing, or you can build a completely different way, where you can make an Earth but much bigger, with a tiny atmosphere, and you have what's called a rocky sphere. So this is where we are, and on the diagram before, it's impossible to see the difference. Because actually all these planets have the same density. You can play with the density, you can play a little bit with the mass and the size, you don't really know what, because the way you build up the planet, I mean, you can end up with a bit like the way you like. And how to make progress into this is trying to find out whether you can detect the atmosphere. So I want to show you briefly what we're doing, and because this is what is going today. So today we are targeting telescopes on some of these objects I've shown you to understand whether they are of that kind or of that kind. And detecting the atmosphere or not is telling us a lot about the structure of the planet. So the trick is the following. When you have a planet in transit, you have these two very special moments. You have the transit, when the planet is in front, and you have the time when the planet is behind, that we call the eclipse. That's the terminology we're using. This is the star right here. Now, if you look with a telescope, imagine you have a telescope looking at the star, right? And you record the flux. So you record the light coming from the star. What you're going to see is something like that. So you have the time here. It's called the orbital phase, because we just synchronize the time with the orbital phase of the planet. You have a time when you have the planet going in front of the star, so it will just make a shadow on the star. So you will lose a little bit of light. This means this light, this is 1, just normalized to 1. So here you're losing a little bit of light, about 2% in that case. And there's a moment when the planet is behind, what we call the secondary eclipse. It makes this kind of light curve. That's the terminology, we call that light curve. Curve of light of the stars. And if you zoom in this, you have this. So if you think a little bit about this light curve, there is two special moments, which is this moment there, which is when the planet is behind the star. It's called the eclipse, remember. So if you imagine now in your head the system, because the planet is behind, it means that's the only moment where your telescope is recording the flux of the star, only. Because the planet is behind, so you don't see the planet. So essentially, this is the flux of the star. So if you imagine, if you understand that this is the flux of the star, up to that point, because that defines the star, all the rest is a planet. This is how we can measure the flux from planet without seeing them directly. We're using this trick. So we use this trick, anything above is a planet. And it means this is a planet dark side, just before the eclipse, and that's a planet day side. And depending on the nature of the planet, the shape is changing here. And you know from that you can find out the temperature of the planet. So we can do more than that actually, because there's a bit of a trick we can play with this kind of techniques. When there is a transit, we can pick up the wavelength where we observe the transit. So to give you an idea what it means, I decided to show you one of these beautiful pictures of the ISS. So there's a picture from the ISS and of the Earth here, and what you're going to see is the moon going behind. So you have to imagine the moon is the star actually, and this is the planet. The Earth is the planet. It's a bit of a trick, but just to give you an idea. What I want you to focus on is a transit here. What we see here is the visible light. So it means we see the Earth with the atmosphere. The visible light is technically what makes the blue sky. It's a Rayleigh scattering. It's about 20 kilometers altitude. So when you go 20 kilometers, you have this Rayleigh scattering. If you start going above this, 40, 50 kilometers, I mean, you start seeing the dark sky. But until 20-ish, 2030, it's still blue-ish. So that's what we see here. Now, if I use an infrared detector, the same kind of technique that is using essentially by the spying satellite, then they don't see that. They see the ground, because they see through the atmosphere, and they see the thermal emission from the ground. So if I move to an infrared, this is what I would see. So it's about the same moment. So you see, we see a planet which is a bit smaller. If I go back, it's a bit bigger. It's a bit smaller. Now I can push and look at the very height, the highest possible of the atmosphere, which is the ozone layer. Ozone layer, it's about 60 kilometers, 60, 70, depends on where you're looking at. And then you use the bandwidth of the ozone, so you really target the ozone. And this is what you would see. It's a bigger planet. So it's just to illustrate the idea that depending the wavelength you would observe the planet, you don't see the same planet. Actually, you see the structure of the atmosphere.
where we know that at the sunset, it's right to the planet. Here we're doing. We call that transit spectroscopy. So with all these techniques, we are making progress into understanding the atmosphere of this planet. And that's, again, being done today. There are people working on that. There's one of the experts, worldwide expert, is working on IOA. It's Niku Madhusudan. He's doing modeling of this atmosphere, and he's retrieving the data from the observation, computing the atmosphere of the planet. Okay, so if I try to summarize, we're detecting small planet, we're measuring the atmosphere. So what's next? Well, next is what can we learn about this atmosphere? Can we learn about something about life? Something about water, about this atmosphere? What does it mean, all this? And I would like to open this chapter. Because anytime you see one of these discoveries being announced about planet like the Earth and so on, there's a lot of excitement on that. And that's for good reason, because I think we are making progresses, but not exactly maybe the way you would understand it. So let me first share with you a concept. This is theoretical calculations of different kind of atmosphere with different assumptions, with the purpose to demonstrate that you produce molecules into atmosphere. So the assumption here is a planet is rocky, right? But then, depending how you make the rocks, depending what you kind of rocky planet you're talking about, the atmosphere could be rather different. Well, interestingly, they all have oxygen. They all produce oxygen. Well, one of them is the Earth. We understand why, because it's life, produce oxygen. But you can also produce oxygen a different way. And we have to remind ourselves, if you break apart the H2O, the water molecule, you're making oxygen as well. If you break apart, you can have even the CO, and you can also break apart and get the oxygen. And if you manage to get the right energy, the right irradiations, and most of this planet are pretty much irradiated. So my message to you here is, I think what is fascinating about this atmospheric study of the planet, it opens a complete new chapter. It's not only about getting obsessed about finding trace of life, it's about trying to understand actually the whole global geophysical nature of the planet we're talking about. And of course, life is part of it. So to elaborate a bit on this chapter, I would like to share with you a couple of results. One of them is from that place, about the origin of life. And then I'm trying to bring all this together and explain to you what we're doing in terms of astrophysical content here. This is one of the, let's say, most advanced modeling right now of the origin of life on Earth. Well, there's a different way to see that. I mean, you may have learned that the origin of life is the bottom of the oceans. Maybe, but recently significant progress has been made with another scenario that is based on the chemistry of the building blocks of life. What are these building blocks of life? Well, one of them is the amino acids. We have these 20 amino acids, and the question is, how do you build up these 20 amino acids? Some of them are easy to be produced in comet, because you use the UV radiations and you can break apart the element you have on the comet, but you don't produce the 20 you need for life. So the idea here is, if you can find out a global chemistry that is producing the amino acid, it may be the beginning of the pathway for life. And it has been done, actually. It's quite recent here. This is one of the first papers. There has been a couple of papers where you use the kind of early Earth. It's a picture of the early Earth here, with water. You need some production for the volcanic activity, SO2, SO3. You need some production for what's called impact, cometary impact. One of them is HCN. I mean, it's full of HCN into comets. So when you have a lot of comets falling in, which is the case early on in the solar systems, you have a lot of HCN. Well, I must admit, it's not the first gas you think about when you think about the origin of life, because HCN here would die all of us, because this cyanuric acid is a little gas. But in terms of chemistry, it has a lot of potential. The atmosphere is nothing special, and that's a big change. If you remember the early work of Yuri Miller, I mean, they used to have a very special atmosphere, very energized, and it's highly reduced, that's what we call. But we don't need that, and we know it's not the case. We know that the early Earth was not like that. Because when you form a planet, essentially you're making an atmosphere of CO2, which is pretty much neutral, so you cannot hope for the atmosphere to help you when you want to form the chemistry. So how do you make a chemistry? So if there's some chemists in the room, we all know that to make chemistry you need to shake, to warm, or to bring a lot of irradiation into it. And shaking is not great. you could imagine a hot vent or something like that in the chemistry, but here the assumption is this is being done on the surface of the planet. And you use the UV radiations you have here. And behind there is a full model here, and I just want to give you an idea what this looks like. And actually this is a network of reactions. It's not only one reaction. There is a lot of network of reactions. And what we did in this paper with one of my colleagues here, we tested some of the reactions because the key assumption is you need energy from light. And the light, you have it for free from the sun. But how much light do you need? And the interesting findings that we demonstrated is the sun at the time when you form the star, our own sun, produced enough UV radiations to produce the right chemistry. And that's not something given, because if you don't have enough energy to make it work, you still make chemistry, but you don't make the chemistry of life. So chemistry is something very tricky, because chemistry always happens. So if you do cooking, if you try to do cooking, you always cook and you always do something. Well, whether it's good or not, it depends exactly how you make it, right? Okay, it's exactly the same here. So the sequence of reaction for the chemistry is exactly the same. So if you have the right amount of energy, you produce what's called a right chemistry that is leading to origin of life. If you don't have enough, you end up with something which is maybe interesting chemistry, but it would end up like a good shampoo at the end. So that's really what it is. It's a competition in the chemistry process, and you need this amount of radiations. And we demonstrated that it works. So the key element of this theory is maybe the origin of life started on the top of the planet. I mean, on the surface of the planet. So that is very interesting because it brings a couple of testable assumptions here. Because we have a series of reactions, we have a series of assumptions, there is a series of elements we need. So let's try to demonstrate that we have them practically. So how can we do that? Well, we have to understand the global model of the origin of life. And I have to bring you back. So you've seen we've been doing astrophysics. So we did a little bit of chemistry, and now I'm dragging you into earth science. Because that is the story of the Earth here. That could be extrapolated in a more general way to any planet, any rocky planet, at least here. So when you form a rocky planet, there is different phases. Essentially, there is four main phases. The first one is this, we call the nebular phase, when you make it. That's the astrophysical bits, when you really assemble the planet and you bring it in. After, there is a very, very exciting moment when the planet is still hot and they receive a lot of impact, a lot of stuff is falling on the planet. You can even imagine having an atmosphere at that time being produced, and then the atmosphere is wiped out because there is a massive impact. The same kind of impact that created the moon in our case. Remember, the moon is a creation, is an early event, about 20 million years old after the formation of the Earth. That a big comet, a really big one, I mean, impacted the Earth and ejected a substantial amount of material, and this material at the end ended up to be the moon. So we have this phase. After some time, everything cools down. The planet starts to cool down. There is all the heavy material is sinking down and making the core. You start up the magnetic field that starts to emerge, to be emerged here. You have a partial melting, and then you keep having the volcanic activity. You produce an atmosphere essentially of CO2. You should have water, whether it comes from the outside, whether it comes from the inside, because you have this partial melting coming out. SO2 is a volcanic activity being produced. And then after some time here, you have the chemistry of life. And you have two ways, whether you produce something visible and life becomes part of the production, life is one of the elements of the planet, or it is not. In this case, you end up with a kind of a mineral planet without any life. So what I'm telling you here is life is part of the planet. Life is part of the process of the planet. So it comes with it, or it doesn't come with it, but it's part of it. And if you want to understand the origin of life, you have to understand the planet. And that's a big challenge that we have in front of us, because we really have to work through everything together. We have to have the chemistry, we have to get the data about what to observe. So what do we observe? Well, this planet has a very different signature depending when I would observe it. Well, to give you an idea, this is the evolution in time of the gas. So this is the amount of gas you have. The oxygen is here. So you started here with almost no oxygen, and then you have this rise of oxygen. Of course, at the same time, you have a drop of the CO2, which, by the way, was a very dramatic event on Earth. Because losing the CO2, you lose the greenhouse effect, and essentially the Earth at that point became a snowball. And it's kind of a miracle that we went out of this region. And what is expected here, may have happened, is maybe a very massive volcanic event, enough to melt and to produce enough, I think, greenhouse gas, have reversed the situations and made the Earth with, at the same time, the oxygen and then sustainable liquid water. So it's a very fascinating moment here. But what you do see here is if you try to translate this atmosphere of the planet in terms of visible feature, you can produce this kind of spectra. This is a spectra of the early Earth called the Archean age of the Earth. And then you have the time when you produce the life, which is there, and you have right now. And we're changing it right now because we're bringing a bit more of CO2 into the atmosphere. So this is essentially the story of the Earth, and it's a story we can observe on other stars, on other planets. So if you have another planet, you can see the same. You will be able to see through this. Depending on the age of the star you're observing, you will be able to say something about that story. Is it always like that? Was it a very unlucky, very unexpected, very rare event, this kind of rise of the oxygen here? We know life happened somewhere here, so life is very early on. But the fact life has been able to keep going is not given. Everybody assumes, well, once you have life, you cannot stop it. Well, it depends what happened with the planet. If the planet becomes unsustainable again for life, you don't have it. So it's not very clear, and we have a couple of good examples next to us. We have Venus next to us, which is pretty obvious that maybe Venus 1 billion years ago was exactly like the Earth. And something happened on Venus and stopped the plate tectonics and then stopped the recycling then of the CO2, and then you ended up with a full greenhouse effect, and that's what it is right now. And it's this idea that the planet is an entity, is a living entity where everything has to go together. It's a fascinating element because we have a lot of stars, almost an infinite number of stars to study, so we can start to project ourselves. So you see the discovery of the planet on the star is not only setting the solar system into a more global scenery, is actually facing our own story in terms of life on this planet. Because we will learn something. How far, I don't know, but we will learn something. We will learn how likely it is to have something similar or not. Of course, related to that, there is a very fascinating process, which is the growth of complexity. So even if you start with something which is nice chemistry, you have to build up, you have to assemble the building blocks when you make life. And is it a pathway which comes without any specific event? Does it come by itself? Or do you need some specific event that's happening at a very specific timing to make it work? You can imagine you start and you stop at some point. Nothing gives you for given that you will reach what we call the Luca right now, which is the common ancestor for all the living life we have on Earth. So this is the kind of question I think that we're starting. We're just starting it right now, but at least we have some element that we can play around and try to put together. And I hope that I share this kind of enthusiasm. What is really happening right now is that stuff. Because Mars is another interesting planet in the sense that Mars has essentially stayed like it was after 1 billion years after the formation of the solar system. So we go back in time by 3.5 billion years by landing on Mars, which is a very fascinating moment because we know that that is at this moment that life is happening on Earth. So by going to Mars, we're going into the past of the Earth, and this past has vanished because of the plate tectonic, the recycling of the continent on Earth. There is zero trace of how Earth was about at that time. We just have few rocks that we can just use, like zircons, that to tell us something about the condition at that time. But we have no idea about the chemistry at that time. So this is why people are very, very excited to go on Mars, because we're testing the chemistry of the origin of life. We're not looking for life. And I know some people believe that we're going to find life on Mars. I don't think they're going to find life on Mars. I think that there is no life, and certainly not within the capability of this mission. There may be life, maybe 1 kilometer downstairs or maybe 100 meters down, I don't know. But at the surface, it's no way. But What is fascinating is the kind of explorations that we will be doing on the chemistry. And this is the J0 crater, where is our robot. And even if you're not a specialist into Earth science, you already guessed what it is. And this is a river flow we're seeing. It is a trace of a past river flow. So the selection of that landing site was very careful. The idea is to land somewhere here, and this is the top of the ridge. There must have been a river here, and there's some kind of lake here, and then by going up through this way, you're exploring different layer of the chemistry, different layer of what may have happened about the origin of life. So when you see that right now, what you have to keep in mind, actually this is the way we're trying to explore. This was exactly the same place, we're talking about that area here. And we're going into the lake. We're going into what remains from the lake. We're going to find something. What? I don't know. And that's a very big challenge. So there is some predictions. So it's not, Mars is not exactly like the Earth, so we cannot make really a carbon copy here. But certainly there will be big surprises. And we will help to add one point on the diagram I've shown you before here. That's the whole idea of Mars. That's why people are quite excited here. So I would like to mention that without going to Mars, there is a couple of locations on Earth that are not very different from Mars. If this is some area here, some of them is in the Altiplano in Southern America, the other are in China. There is a couple of places that have similar geophysical conditions, and it doesn't look very much alive here. You see that? Well, there are plenty of life in these places because life is everywhere on Earth. But just to give you an idea that it is interesting as well to look at the Earth as a reference. But use it as a reference. We have a lot of interesting geophysics here going on, and we can compare and reflect what we have found on Earth on what we're going to find on Mars. So the Mars exploration, especially the sample return, that will allow to use all the amazing equipment we have to study in great detail all these rocks, is going to open up surprises. And be ready to be surprised here. And people are very excited by this idea. We have to wait 10 years, but 10 years is nothing into science. Now, what I would like to mention a little bit here is the astronomy perspective into this. So I think you understand, so we're working on different fronts here, the origin of life on Earth, exploring a kind of time stamp which is Mars, but also we're not giving up the idea to see some of the specific episodes of the origin of life on Earth on other planets. How do we do that? Well, I'm coming back to my diagram before. Let's imagine that you have an equipment that can measure this kind of atmosphere. Well, we don't have yet this, we barely have it for small planets. With the James Webb Space Telescope that will be launched soon, we may be closer to that range, but it will not be enough. We need the next generation of space equipment. It's going to happen. I mean, people are talking about doing something way more difficult, like going to Mars. But flying a slightly bigger telescope, it's not that difficult compared to having a base on Mars. But the key here is you have to imagine that, I give you 3 examples, which is the timeline of the Earth. Well, you can play with that. You can change the timeline. You can change the history of the Earth according to different criteria. And let's imagine you play a little bit with the chemistry of the Earth. You play a little bit with the amount of energy you have. You play a little bit with the number of impact you have. You can play with the chemistry of the major impact that is going to remove or affect the atmosphere, and of course you can change the history of the volcanic activities. Any of these specific event has a traces that can be modeled and expected into a planet, and that's exactly what we're trying to do here. So we can look at different wavelengths and pick up different kind of molecules. So this is really the key here. If people are talking to you about detecting life with the oxygen, I think this is something, it means that they're not up to date on the question right now. The question is not about this. The question is trying to look at many molecules, oxygen certainly being one of them, but not the only one, to understand what's going on. Of course we need water, we need all this, and water could be quite easy to find, but water means nothing. You have water on the planet, and so what? Okay, you have water, that's a good start, but that's not, you don't really understand what you're doing. So you need to get way more than that, and this is to give you a hint that depending on the episode that is happening on the planet, you have specific traces. Well, there's a couple of episodes that we have not mentioned here, but I would like to share it with you, is the episode of an advanced civilizations. Of course, we are changing the Earth right now, and you can imagine in 500 years or 1,000 years, if we go there, we will have changed the atmosphere quite substantially. In a similar way that we are changing the ground surface of the planet. I mean, look at the surface 1,000 years ago, and it was not the same. I mean, much more forest, completely different. So we are terraforming since quite some time. It's not only new. I mean, we're talking about global warming, and which is really a serious problem right now. But the problem of terraforming the Earth started 1,000 years ago, when we started to grow as a species, and then to plant vegetables and to have herds and all this, and that all this has an impact on the planet. Well, you can imagine a very massive impact when we have a thermonuclear war on the planet, and then it will leave some traces as well. So all this is something that is scary in a way. That's something that is a possibility as well in terms of possibilities in the future. It's something we can look at. So this idea of looking about other planets is very profound, essentially, because you're not only touching the origin of life on Earth, but you're also trying to get the complete scenery where it's fitting in terms of a live species into the global universe, which is something we have really no idea. It's a bit like the fish in the aquarium, trying to think what does the aquarium look like from the outside. It's a bit the same kind of idea. So I would like to end my talk by mentioning that there is a lot of activity in this very university going on. So we have a website. You can have a look, which is the Cambridge Initiative for Planetary Science and Life in the Universe. We are bringing a lot of different departments together, including Art of Humanities as well, because we do believe this is interesting enough, and Cambridge is very special in the sense that everybody knows everybody because of the college systems and all this kind of society around. There is really enough momentum to try to do that together with the people interested. So if you're interested to see if there are opportunities for you, just have a look at the website. We have a Twitter. You can follow when we have something, seminars. So we're planning a couple of seminars that will start on that. We have a launch event planned for November on this, and we are trying to get a lot of money to make something even bigger with more opportunities. So the reason why we do that is because we do believe it's a global problem we're trying to solve here that is bridging chemistry, physics or astrophysics and earth sciences, and all the connection you have here is trying to understand the Earth and trying to understand the origin of life on Earth. And it's not enough. There's a context, which is what about the understanding of what we're talking about. It's called the philosophical implications, all the question about the mathematics of life. There's a lot of model about the way life is evolving, so it's very interesting work on that. There's also the questions of how do you communicate between different disciplines, the jargon, fighting the jargons, trying to communicate in terms of media. That's something we are very interested about. And we have also a lot of people with us interested about what's called the philosophical implications and the terminology. Because when you do science, it's something you may not really realize right now. We have implicit assumptions by just the word we're using. When we say life, well, what does it mean? So we all have an idea of life, and then of course, even if you maintain your mind very open, you implicitly making assumptions here. And we're trying to target that as well, opening a chapter which is about concept definitions and also challenging what is the traditional understanding. So it means we may go back to the literatures and exploring some different concepts. So all this is what's going on right now in Cambridge. So if you want to know this, want to know what's going on, just follow this, the Twitter, or have a look at the website. So I will stop here, and I hope you understand that it's quite fun, it's quite exciting domain. So even 25 years after the first planet, it's just the beginning of something, which is now exploring the universe in a more global sense. Thank you very much.
Okay, thank you so much, Professor Queloz, for the wonderful talk. As a token of our appreciation, the committee would like to present you with a little gift.
Oh, thank you. That's lovely, thank you.
It's a little paperweight
Okay.
with our logo.
So you have time for some questions if the audience wants to ask some questions.
Yeah, if anyone has a question, just shout it out now.
So you were talking about how to protect the transit rates of planets, big transits and whatnot. How would a twin planetary system
the configuration you're talking is very likely to be unstable. So you have to maintain some stability into the systems. What has been detected and can be detected is a planet orbiting 2 stars. So there's a couple of binary stars, very close, and planet orbiting binary stars. So that has been found, or it's possible. Now, to have a multiple system planet, we have some, but if they share the same orbit, actually this is highly unstable. There's very few configurations where you maintain stability. In the solar system, there's 2 regions, and you can work out the stability regime where it is. And there is some possibility to be along the orbit and have another planet as well on the same orbit, a very specific configuration. But there is condition for this to happen. We have been looking for that because it is possible, in theory, it's possible. It can be found. It has not been found. So it means if it exists, it's very rare. But it cannot be discarded, and I think it would be really cool to find some, because technically it's possible to find it. But as of today, we have not found any. And we have tried for some of the system because we know it's possible.
Any other questions?
Is there a limit on the sort of sizes, minimum sizes you can detect of various exoplanets? Like, if there was, say, a planet like Mercury, an exoplanet star, or even smaller than that, would you, with the methods you have, would you be able to detect that?
Well, you've seen the limit. I mean, I just overlay the limit. So of course we have limits, and the smaller the planet, the more challenging it is. And when we have long period, well, very long, it could become easier in some other way. But of course, there's plenty of limits, and all this, the way we understand the populations, call it the population of planet, it's incomplete right now. And that's why nobody believes that we are the only planet, exactly like the Earth in the universe. There must be other planets like that, and there's a push to go in these directions. What you need is a new development here, and it's always the same. I mean, when you start a new field, you have this kind of time when the low-hanging fruits are there. So you just pick them up, and then you have to work a bit harder to get to the next stage. And people are working quite harder right now, trying to push, so there's a new generation of space survey being designed. One of them is called Plato, that will be flying in 3 years. We're developing a new generation of equipment on the ground to detect these tiny planets, but we know it's going to take years of data because we need to collect way more data. So we're looking for these systems. We do believe they exist. Practically, you see in the solar systems that you have all the size possible. So you can extrapolate, you have everything you need. And it's easier to have a small object, to build up a small object than to build up a massive one because of the timing to make it. So you would expect quite a lot. But there may be other reason in the formation sequencing that prevents maybe some planet to exist. And because we're so much challenged right now with the kind of a theory of the formation for the solar system, that people are a bit reluctant to make too many predictions because of course you can use the solar system as an example, but it turns out that most of the planets are not like this one. So until we really have enough understood this and make some progress on the structure of this planet, and we are making progress right now, we're getting more precise and increasing our understanding of the density, the modeling is better, the simulation, when we form a planet, people are able to simulate with way more detail and to realize that it's highly nonlinear, you have a kind of nonlinear effect when you form a planet. All this has to be accounted, and my hope that there will be a point when we have enough understanding to make some kind of predictions and understand what is the likelihood of. But right now we're just trying a bit behind that. It's difficult. Where's my chair? You have to look at the chair.